I have to start off. I have a much more socialist view of the world than just presented. Part of it is I'm just older than many of you, but you're all, we've had some excellent talks so far, so, I get to give a talk here with a name after it. I need to turn the thing on, that's right.
It's on, it's just that it's not.
No, it wasn't on. Can you hear me better now?
Yes.
Okay. So, I was asked to talk, I'm part of the liquid crystal thing, but you can see from the title of my talk that I'm not going to talk about liquid crystals. That's partially because I got sucked into looking at jam systems that then developed into all kinds of interesting mathematical problems related to the elasticity of structures that are on the verge of collapse. And this really is an appropriate place to talk about this because there's some quite elegant mathematics that will, in a sense, join this jamming thing, which has to do with packing of spheres and when they have shear moduli, to topological phonons, which really one can argue is the most exciting thing going on in hard condensed matter right now. And it's very interesting that starting with jamming, you end up with ideas that turn out to be really the same that are in the topological insulators. Now, I will say that the topological phonon stuff that I'll be talking about is so new, there's not a preprint, and there are lots of questions I have about it, so you may be asking me the same questions I'm asking myself, and so I might have to give you an answer that, well, in a couple of months I'll know the answer. Right? So what I'm going to do is to talk about what nearly floppy materials are, what I mean by materials that are on the verge of mechanical collapse. And the hero of this really is James Clerk Maxwell, who in 1864 wrote the first paper about this. And it's interesting to visit at least some mechanical engineering departments where you mention Maxwell, they think of this first. They don't think of statistical mechanics or of Maxwell's equations. They think of stability of networks. Then I'll review the phenomenology of jamming. And then I'll talk about these periodic lattices, which are close in spirit to the point where systems first become jammed. Then I'm going to talk about a particular lattice, the twisted Kagame lattice, which surprised me to death, and that gave me the insight then to convince Charlie Kane that we should look at topological things. I should mention here that this work was done with my former postdoc, Xiaoming Mao, who's at Michigan now. I got her husband as a postdoc for free, who figured out some of the things, and Anton Suslov, who was a former graduate student. And then the real star of this part is Charlie Kane, who invented the whole thing and happens to have an office not far from mine. So, jamming is really, you can go on on ISI, the Web of Science, and find that, there are thousands of citations to jamming. You have to be a little careful because if you do jamming in ISI, you actually get jam, which you eat sometimes, which is not the same thing. And then there are topological insulators, and these periodic isostatic lattices I'm going to talk about really join these two with some quite elegant mathematics. So this is the appropriate place to talk about it. This encapsulates a little bit of what I'm going to talk about. These are the various Kagame lattices. There's surface waves and things like that. And PNAS had the poor sense not to put this on their cover. So we're going to go back to 1848. The Industrial Revolution is in full swing, and people are building bridges. This is the Warren Truss, patented in 1848. It's a bunch of triangles like this, and this happens to be a system where if you specify the forces at the nodes, you can get the stresses in the links without doing any elasticity. And that's I don't know. When I was a freshman, we had to use virtual work to solve what the stresses and forces were, but they never put a crosslink here such that you had to consider the elasticity of the beams. And you see this motif throughout architecture. There's the Hancock Tower in Chicago. Now, in the condensed matter context, we have lattices which, at least in appropriate model limits, are very similar to those isostatic things. So if you take the square lattice with springs connecting nearest neighbors, ignore the crosses, which are the next nearest neighbors, then you have a system that's on the verge of instability. In fact, if you have a finite version of it, you know that if you do that, the thing will just collapse, right? It will not support itself. The same is true of the Kagame lattice. Well, the Kagame lattice is different. It has the same local structure. Each site here, if I'm under periodic conditions, has 4 neighbors. Each site in the Kagame lattice also has 4 neighbors if you don't add next nearest neighbor forces. This one, curiously enough, will support itself, but it has modes of collapse that will, if you tickle them, they'll make the whole thing collapse. Here is a lattice that's way under-coordinated. The diamond lattice has 4 neighbors per site. And this thing is unstable unless you put in the bending forces, which are inherent in a quantum mechanical description of the carbons. But if you're just putting in springs, you wouldn't do that. So you need bending forces. And this, of course, becomes, well, then there's this network glass cristabolite, which is silicon and oxygen in a random pattern. And here, this sort of mimics this structure, which is the pyrochlor lattice, where each site has 6 neighbors, rather. It's connected to 2 tetrahedra, each of which has 3 sites on it. So those are the kind of lattices I'll be talking about. Now, a place where this question of rigidity and stability of a lattice comes up is in the rigidity percolation problem. So this is very well studied in the 80s, which followed a lot of work in the 70s on the percolation problem itself. So if you take a lattice like this, a triangular lattice, and you randomly remove bonds, and you make the bonds be resistors, then at a critical concentration, you lose paths across the sample, and the thing becomes non-conducting, and so the conductivity of the lattice grows continuously above a threshold PC. Now, if instead of putting in resistors, you put in springs, then the full lattice is clearly stable. It will support shear and compression. But as you dilute, eventually you'll reach a point where you don't have a way of communicating the elastic stress across the whole sample, and you have another percolation threshold. And it turns out that in this 2-dimensional case, at least, you have behavior that's very similar to the resistor network, where the shear modulus grows as P minus the critical concentration PC to power T, and there's a probability of being in the connected cluster that grows as P minus PC to the beta. And so all of these people spent a lot of time in the 80s figuring this out. And you can go and do it in 3 dimensions as well. Now, more recently, people have come back to the problem of packing of spheres. So you may have noticed that I was telling you that the critical lattices in 2 dimensions had 4 neighbors per site, and the critical lattices in 3 dimensions had 6 neighbors per site. So if you take a bunch of spheres and shake them up in a bag, they don't crystallize into a nice regular pattern. If you look at the number of neighbors each sphere has on average, it's equal to 6. And then if you compress it a little bit further, if the spheres are not perfectly rigid, so they can squeeze a little and they have elastic restoring forces, then they develop a few more neighbors and they have a non-vanishing shear modulus. So this thing is constructed, because it's constructed by shaking, so that it will support compressional forces like that and like that, but it won't support a shear where you take the bottom and move it relative to the top like that until you compress it more. So this thing actually has, on average, at the critical point where you go from being separated and disordered to squished together and ordered, a state which has this critical number of sites of neighbors of 6. There are variants of this which have made the press recently. The New York Times a couple of years ago. This is Paul Chaikin, the co-author of my book, who, He's changed? Oh, yeah. That's what happens when you spend too much time doing physics, right? Which is what he does. But he's always, if you go into his office, he has this 55-gallon drum, oil drum, and you look at it and it's filled with M&Ms. You've been there. And he always tests how intelligent you are by saying, well, is that thing full or not? And of course, there are 2 answers to that. How would you find out how full it is? Oh, you can't pick it up. Come on, if it's full, you can't. It's 55 gallons. So Paul's answer is you stick your hand in, right? See how far down it goes. My answer was you click it like that, and if it rings, it's not full. And he didn't like that answer. Anyhow, he's had a long-standing interest in M&Ms, and so he had to do an undergraduate project, so he had the undergraduates, throw them into a sphere like that and do the packing, and found that they packed more densely, a greater volume fraction when they're in this jammed state than the spheres, and that really generated a lot of things. And there's an interesting story to tell about that if somebody wants to hear it later. But let's now think about ways of doing this on a computer. You take spheres, you put a bunch of points down at random, either in 3 dimensions or in 2 dimensions. There's a figure in 2 dimensions. And you start expanding the radius of these points until they just touch, right? And then you relax and so forth until that point where you can't put any more in without compressing the system. and that then gives you 2. So this is right at the point J. This is the temperature 0, and then you squeeze it a little bit, and you get these force chains and so forth. So that's the jamming transition. So now that you've gotten the general picture of what we're going to look at, I'll look at the outline again. I'm going to focus on mostly the 0 modes of the system, but in general, I'm going to be interested in what are the phonon modes, and what are the density of states, and how do they vary as you change the structure of these systems. Then I'm going to talk about how, what jamming has to say about that, and then I'll move to the periodic lattices and to nearly isostatic. So these ones that are right at the critical point are called isostatic for reasons I'll explain in a moment. Then I'll talk about topological insulators and how the topological surface states of insulators are related to the surface 0 modes of these periodic structures. So first, let's go to Maxwell. So 1864, Maxwell was interested in, are these bridges stable? When are they? In fact, he actually cites the Warren-Struss in his paper that I mentioned. And he did the simplest possible thing. He said, let's imagine that each of the points, the joining points of those struts are mechanical points, and we aren't going to worry about rotation. So each point has a degree of freedom for each direction. So if I don't have any struts, and there are n sites, then there are dn 0 degrees of freedom that have 0 energy. Each strut I add binds things together so they can't move along the parallel direction of the strut, and that reduces the number of 0 mode degrees of freedom that there are. So a good estimate of the number of 0 energy distortions of the system is just the spatial dimension times the number of sites minus the number of constraints. And when this is equal to 0, you have the number of constraints is equal to dn. And if you have an extended structure, then the number of constraints is half the number of average number of nearest neighbors times the number of sites. So then this condition that nc equals dn becomes that zc is equal to 2d. And that's if you have a system that goes on forever and ever, and you have to worry about surface effects. So let's just look at this simple system right here. Here's a system which has 7 sites, and 6 sites, right? 6 sites and 7 bonds. So if you use Maxwell's count, 2n minus nc is 5. I should have 5 0 modes. Now there are 2 trivial translation modes, like this and like that, and a trivial rigid rotation mode, because it's not connected to anything. And then there need to be 2 more. So you can do this and stretch it over like that without changing the length of any of these bonds, or I can rotate this triangle down here to give me a total of 2. So I have the 3 trivial 0 modes and 2 internal floppy modes. Floppy meaning, and these are the ones that cause the system to collapse if you were to excite it. So let's go back to the Warren girder. So here I learned this from Simon Guest in the mechanical engineering department here. So a typical bridge has a point here where it grabs the end and fixes that, so it can't move up or down. And at the other end, it has a set of wheels that allow it to move back and forth like this, but it's clamped so it can't move upward and downward. And so if I count the number of bonds, it's twice the number of sites plus 1, where I don't count this site and I don't count this site. The number of degrees of freedom of the system, of the sites, is 2n, where I'm only counting the red guys, plus the 1, which accounts for the fact that this thing can move back and forth like that. And you can see that when you go through this, that n free minus nb is equal to 0, so there are no 0 modes in the system. And in fact, what that means now, since these 2 are the same, I can relate the forces on the nodes to the stresses on the sites. So the stresses are all central force, so they're only along the direction joining the 2 sites. So let's let T be the n-dimensional, nb-dimensional vector of the tensions, and F is the n-free dimensional vector of the forces. And this equilibrium matrix is a square n by n matrix such that if I multiply Q times the tensions, I get the force. And I can invert this by so when I invert this, I can get the tensions in terms of the force, because this is a nice invertible matrix. So that's what it means that it's statically determinate. If I give you the forces, I know what the stresses are. So get this into your head for the moment, because we're going to see this again and again as we go forward. It plays a very important role in what's going on. Yeah. No, each site can go any of 2 directions. So there are 2 directions of the force. but the stresses in the bonds are only along their line, right? Okay. So that's normally it's 2n minus nb. Because I'm at the isostatic point. In general, they're not. If it's lower than that, I have lots of zero modes. If it's greater than that, I have more states of self-stress, which I'm going to talk about now. Now, I simplified things a little bit by looking at the case where n0 is positive. But let's look at what happens. Let me look at this example. You can read this one as I explain this one. So here, suppose I have a square without any diagonal things. Then I have 6 sites, and I have 1, 2, 3, 4, 5, 6, 7 bonds. How did I get 9? Oh, 7 bonds if I don't have these things, right? And then I would have 5 zero modes. And the zero modes are basically that I can move, the non-trivial zero modes are the ones where I can move these things up or down. Right? So let's start adding extra bonds. So I add these 2 extra ones, and I get up to the number of bonds is 9. And so then I have 3 degrees of zero modes, and that's just the trivial rigid rotations and translations of this. But suppose I'd put this bond here instead of here. Now I still have a zero mode, and the count goes wrong. But there's something special about this square. I can put every one of the outer parts of the square, the bonds under tension, and put the crossbars under compression without having any force on the nodes. So this thing has the possibility of supporting structures where, even though the force is 0 at the nodes, there's no compression or expansion or tension in the bonds. Excuse me, there's tension and compression in the bonds, but no forces in the nodes. So we call that a state of self-stress, and you modify the simple Maxwell relation to say that the number of zero modes is dn minus the number of constraints, the number of bonds, plus the number of states of self-stress. And this is a theorem. It's more than a picture. It's a theorem. I'll just put it up here for you to think about. But as long as you're looking at only the harmonic degrees of freedom, in other words, I'm not looking at large distortions, I'm just looking at small distortions about the point, then you can prove this relation from the rank nullity theorem. There are 2 things I want to observe about it. So we just talked about Q being the tensor that relates the tensions to the forces. Okay? Now suppose this matrix has a null space. What that means is I multiply this matrix times a non-zero vector, and I get 0 over here. So you can see that the null space of this is giving me the set of states for which I can have tensions in the bonds, or tensions in the bonds, without having any forces. You can prove that the transpose of this is the compatibility matrix, which relates displacements of the bonds to extensions of the bonds. So this is a force relation, this is a geometric relation, and the standard energy of our system, the dynamical matrix, is a spring constant times QQ transpose. This is assuming harmonics. Well, I'm doing a harmonic expansion about the point, right? And so the harmonic springs comes from this part. But if it's infinitesimal, I'm okay, right? So this is the relation I want you to remember, is that there is the null space is determined by, rather the states of self-stress, or the null space of this guy. The states of zero extension are this guy. So if I have a set of displacements of u, and if C multiplies u and that's equal to 0, then the null space of this, which is Q transpose, are the state of zero modes of the system, zero displacements of the system. Okay, so try to keep that in mind because it's going to appear again. So let's go to the jamming transition. This goes back to Liu and Nagel in 1998, and since then there are thousands and thousands of papers that have been written. Basically, they look at a jam state as like a glassy state, and there's this phase diagram where as you come down in temperature, equal to 0 and stress equal to 0, at the point at which you first touch, which I described earlier, is called the point J. And it's like a critical point in the sense that there are properties on this side, in other words, higher density, that continuously attach to that. Yes?
Can you turn it on again, please?
Is it off? I think it's worse than off. Dead. Oh, there we go. So let's, so phi c is the...
Off
It's
again.
off again. No. Let's shout.
No, no, I'm recording.
I mean, you mean you're gonna have to wait?
I need to be recharged, yeah. What I need is some water. There we go. There's water on the table. No, 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 no.
Except with microphone.
So you have that the number of nearest neighbors grows as volume fraction minus the critical volume fraction of the 1/2. The shear modulus grows as delta z. The bulk modulus jumps discontinuously from 0 just below the jamming point to b just above it. And you can extract characteristic frequencies in a manner I'll explain shortly. A characteristic frequency that grows as delta z, a length scale that grows as 1 over omega c, or as delta z to the minus 1. So we want to observe these things as we move forward with more complicated things. So this is the, just to give you an idea of how this goes, this is the density of states as a function of frequency with increasing delta z. So the black line, which is the straight one, is as close as you can get numerically, basically, to the jamming point. And this one at 10 to the minus 2 is this one down here. Now generally, let's see how this all comes on. So in a homogeneous medium, an elastic medium that supports the shear stresses, the density of states should go like omega to the d minus 1. In other words, in this long log plot, you should see a straight line going down to 0. On the other hand, oops, I see. I'm supposed to do these tricks, right? On the other hand, the density of states of a one-dimensional system is flat at q equals 0. So what we're getting as we increase delta z is we're going from flat to more and more the distribution that you get in a higher dimensional system. And you can, so down here we have essentially Debye. Here we have this characteristic one-dimensional behavior, which is, we'll see, is what you get right at jamming. And the point where they cross is omega star. And it turns out to have this behavior. So one of the things you'd like to understand is, can you explain this in terms of the sort of apparatus that we use for critical points? So there's a cutting argument that is basically right due to Mathieu Viard, and it's really something you can put in your pocket. Let's assume I have a large homogeneous system in which delta z, the total average number of neighbors, is the critical one, which is d, 2d rather, plus a delta z. So inside here, we have an excess of connections relative to the critical point. So extra bonds in this, we're going to cut out a circle here of radius L star. In there, we have an extra set of bonds relative to the critical point of L to the d delta z. But we've cut bonds on the boundary, and there are a number L to the d minus 1 of those, where d is the dimension. So the isostatic length comes just from comparing these two things, and you get L star goes like 1 over delta z. Now, what does that mean? So if the system is exactly at the isostatic point, you expect there to be 0 modes. And if you're at L less than L star, let's see. Right. So if delta z is 0, there are L to the d minus 1 0 modes from the free boundary. In the uncut sample, these modes acquire a frequency of 1 over L. So you take something that you have a bunch of 0 modes in the cut system, you put it together with all the others, that then restricts the wave number to be 1 over L or higher, so you get a frequency that goes like 1 over L. So the number of modes per unit volume, the density of states, is 1 over the volume, the number of modes you have divided by the frequency, and you get a constant. So what we have then is for L greater than L star, wow, for L greater than L star, we have a d-dimensional elastic continuous medium. And for L less than L star, we have floppy modes. I think I've got this backwards here, these two things. It's amazing how you read things 6 or 8 times, you still don't get it. Anyhow, low frequency, you have the at higher frequency, you have the behavior that's characteristic of an isostatic system at a length scale less than L star. At lower frequency, you have the modes coming down in the Debye form. I hope that's clear. It is right. So let's go to the square lattice where you can do everything exactly. So I put this in under periodic boundary conditions. Then every site has exactly 4 neighbors. So I'm exactly at the isostatic point that Maxwell talks about. And you can then say, well, unless I have states of self-stress, I don't have any 0 modes. And so you can, but in the finite lattice, you can do a count and find that you have nx plus ny extra cut bonds on the surface. So in the finite lattice, you should have nx plus ny 0 modes. And that actually works because there are no states of self-stress in the system. But if you actually calculate, here is the dynamical matrix. And you can see that if I set qy equal to 0, let's see, if I set qy equal to 0, then I have all of these modes in qx that have 0 frequency. So here I set qy equal to 0, and I ask about the mode that's polarized in this direction. For every qx, there's a 0. So actually, the mode structure of the periodic square lattice has exactly nx plus ny 0 modes. 0 modes, which correspond to moving exactly the 0 modes of the finite system, where you move a whole line of atoms infinitesimally. So you don't change the lengths of these bonds, of the vertical bonds, and you don't change the length of any of these bonds, at least to order u squared. So you get a one-dimensional density of states, and you have a set of 0 modes. And so this one-dimensional density of states looks very similar to what we have at the jamming transition. In addition, you get that the shear moduli vanish, and the bulk modulus is proportional to the spring constant. Now, what happens if I add next nearest neighbors? So we can move away then from this critical point where we have exactly the Maxwell condition by adding next nearest neighbor springs. If I do that, I've increased the number of neighbors enough that I'm going to have a system that is rigid and has no 0 modes except for the trivial ones. And you can calculate the band structure. You have a Brillouin zone. You can go from gamma to m, or you can go up to r. So if I go from gamma to m, if I have no next nearest neighbor forces, I have a straight line of 0 modes. I think everybody's probably getting a little hot in here. Can we open this door again? Or is that going to be too? Yeah. Does that feel better? Yeah. So, here's the line of 0 modes that I talked about. There's one for each q along there, so that gives us what we expect. And of course, that means, since we have 0 modes when there's no next nearest neighbors, that we have to have states of self-stress. Well, you do. You take this square lattice, you wrap it around, and every bond is connected to another. So I can put any line under stress in such a way that there's no force on the bonds. On the sites, right? So that's what's the definition of a state of self-stress is. When I add the next nearest neighbor forces, we get a gap in the spectrum at m. So here, this is going from gamma to m, which is from here to here. I have basically a phonon structure, and there's a gap everywhere except at 0. And if I plot from m to r, that's what this is. In the absence of next nearest neighbors, I have these, basically this V-shaped spectrum with a linear dispersion going from here to here. And I turn on the next nearest neighbors, and I get a gap. So from that, you can calculate a characteristic frequency, which is twice the square root of k prime. That's the gap here. And there is a characteristic length, which goes like k over k prime. And you can see that this characteristic length is basically 1 over the characteristic frequency, which is what we had at jamming. And you can actually, the cutting argument works perfectly well here. If I'm have a very small sample, then I'm at, if I cut out a small part of the periodic system, then the actual dispersion follows very closely that of the isostatic lattice. On the other hand, if I'm much larger, then I see the gap. So just by looking at this picture, you get exactly what Viart predicted. And one of the reasons is that the states of self-stress are the same, really, as the displacements of the lattice without a boundary. OK, so let's go to the Kagame lattice. You have the same thing. Here, I've drawn in the 0 modes because it's less known. But I start off with lines that go in the 3 symmetry directions. And each of those lines can support a state of self-stress. So there is 1 0 mode per line. And that then gives you, a bunch of 0 modes in the periodic spectrum. And these modes, the way to think about this is, if I look along this line, from here to here is 1 unit cell. And along the line, there are 2 atoms per unit cell. So for each value of qy in this direction, there is an independent mode which corresponds to taking this line and moving this point up and that point down, which then rotates the triangles in such a way that to harmonic order, I don't change the lengths. So I have a 0 mode for every one of the lines going around, and they look like that. It's interesting that unlike the square lattice, if you calculate the shear and bulk moduli of these things, even without next nearest neighbors, it's non-zero. And that has to do with the fact that I have straight lines that go in 3 directions, and a straight line by itself to harmonic order will both support compression like this. And if I have a line like this and I try to pull this over that way, keeping the distance this direction the same, I actually stretch the lattice. So even though there are a number of 0 modes proportional to the square root of numbers sites, it still supports macroscopic stress and strain. Yeah.
Indeed, even the cutting argument, if I understand correctly, you never need to put disorder in this argument.
So it works very cleanly for this. In fact, it's cleaner than the...
There's something that you miss from the fact that these discussions are all about ordered systems.
Well, OK, so let's go to the next slide. So I'll answer the question in just a moment. So here we get to do the same thing, going from gamma to m. There is a 0 if I don't have any next nearest neighbor forces. Next nearest neighbor I put in, I get a gap. And so for every one of these symmetry directions coming along like that and like that, I have a 0 mode. And if I go along there, I see we have a 0 mode in the, yes. And so for each of the directions, I can again calculate what the frequencies are. And again, there is a correlation length which scales as 1 over the square root of k prime, and a frequency that scales as square root of k prime. So again, I'm getting L goes like 1 over omega star. Now, you'd like, as we just heard, I haven't done anything random. Well, how would I do a random problem? So we're going to start with the absolutely periodic isostatic system, and we're going to randomly add next nearest neighbor springs. So we're going to add next nearest neighbor springs with a probability p. So I now no longer have a homogeneous system. I have a random system. And there's a well-defined approximation that really works very well called the effective medium theory, or the CPA, depending on where you're coming from. Basically, you look at each bond, and you choose and you replace it by an effective bond such that the scattering from a random bond is 0 in the effective medium. And when you do that, you find that the effective next nearest neighbor spring constant at 0 frequency scales not as the probability, which you might have expected. You would have thought if you're doing an average thing and you just put things down at random, that the average elastic or spring constant would just be the probability that's there times its strength. But no, the calculation gives p squared, which gives that this k goes as z minus zc squared. And remember that now I have an effective medium, so the omega star is the square root of this next nearest neighbor effective spring constant. It goes like delta z. And the same thing for the length. So this effective medium then gives you exactly what you get for the jamming when you replace, when you scale things with delta z. Furthermore, the density of states of this is for the square lattice, for the non-random system has a strong Van Hove singularity at basically omega star. You put in the randomness, and the density of states does exactly what you got for jamming. So this clearly has many of the properties of jamming, and one can explore that further. But there's another interesting question about these. You know, I started off, yes.
You might, however, worry, and it's kind of very similar to mean field theory in many ways, right?
You might. You might.
Worry about whether
so,
the
the blue dots are the effective medium theory. The red dots are simulations. So it's pretty good. You might worry, but it really works much better. And it certainly, there are many other instances we've done now where it fits simulations. It works particularly well on you know, if you put in bending and you dilute the Kagame lattice, you get the things that are, you know, described fairly well, the effects of adding bending.
The thing you were comparing wasn't singular condition, right?
This is non-random.
Mm-hmm.
This is random.
Oh.
So the random, you know, doing the CPA both matches the simulations and pretty closely what you see in the jamming problem, the jamming problem itself. Okay. Oops. So now there's a, you know, I started off doing this like a physicist. Let's just look at the models we know, the square lattice and the Kagame lattice. But remember, the minute you say that I have all these floppy modes, then you can take these lattices and distort them in an infinite number of ways. And it's interesting to ask what happens if you have another structure. So I instructed my student Suslov to go off and find other versions of this structure. So the first one we came up with was with this. And I have to tell you that we thought we had discovered this. I spent hours on the web of knowledge trying to see if anyone had done this. I found this finally, which is in an obscure proceeding, but I'm sure that people like Simon knew about it, but it really was hard to find. We couldn't find it. But we were looking in the wrong place. So for first here, this is a class we're going to look at. I call this the twisted Kagame. All you do is take any pair of triangles and you twist them so that there's this angle, rather than being a 0, is some angle non-zero, right? And already you can see there's something interesting about this. All I'm doing is increasing that angle when I go from here to here to here. I decrease the total area, and in the process I decrease lengths in both parallel and perpendicular directions without changing the length of any bond. So then you can take this and ask questions of what is the phonon structure of that system. I should say that I was looking in the wrong place for this. It turns out that the architects have known about this structure for a long time. So if you want to see an interesting series of pictures, look for Ron Resch origami. And he has all of these structures that he's using in architecture to create nice, you know, curved surfaces for buildings and so forth. And you can see it's exactly that. In fact, it gives you a prescription for how you bend the origami. When you push it in, the hexagons get pushed inward, and the triangles get pushed like that when you pull it out. And actually, it's the first example of a negative Poisson ratio that I've seen. You take any crumpled paper, and you pull it like that. As you pull it out, it gets smaller, and as you push it in, it gets right. So it has a negative Poisson ratio, and that's just a regular version of it. Oh, but you know, you can make it structurally sound. Actually, he has lots of ideas because you're starting with pieces that all have the same shape. Then you can put them together in such a way to create a nice form. I would show you a movie, but you don't need to see that. Okay. So you saw that as the thing compresses, it compresses uniformly in all directions. So if I push on it like this, it compresses in that direction. Or if I pull one of the other ones like this, it expands in the other direction. That's not something we're used to. We're used to systems that are nearly incompressible, so that if I pull like this, what we expect, we take something like that and we pull in a vertical direction, we expect it its length in a perpendicular direction to decrease so that we keep the volume the same, or approximately the same. Here we have the opposite. We start with this, we pull on it, and it grows in the other direction. And you can calculate this Poisson ratio, which is the ratio of uxx to minus uzz. And for a two-dimensional system, it's the bulk modulus minus the shear modulus divided by the sum. And we just saw that this system has a vanishing bulk modulus because I can change its volume continuously without any change in the lengths of any of the bonds. So the energy associated with compression is 0, which means the bulk modulus is 0, which means necessarily we have a negative Poisson ratio. And these systems are called negative Poisson ratio, or they have a fancy name, auxetic. And the classic example of an auxetic system is the inverted honeycomb lattice, which is right here. If you look at this bow tie in the middle and you expanded it out so this was on that side and that was on the other side, you would have a lattice of hexagonal cells, which is the honeycomb lattice. And obviously, if you pull this one out like that, it will tend to push this way and that way, and you get an expansion in the other direction. So, you know, the world's expert on this is Rod Lakes at Wisconsin, and he's actually made a three-dimensional auxetic foam by starting with a foam, compressing it, and then cross-linking it in such a way that you lock in the three-dimensional version of these things, and it's actually isotropic. So you can calculate if you turn on K prime, there's a region of negative Poisson ratio and a region of positive Poisson ratio for that simple model. And you know, we actually have started thinking about doing this at Penn. We have Xu Yang, who can do anything with polymers. So this shows a standard Kagame lattice under compression, and it has a bending modulus rather than a next nearest neighbor force. And it can't decide as it's being compressed which way to go, so you get some things that compress and stretch out in this direction, and some that do it in the opposite direction. These right here, and you get, you know, this sort of herringbone structure. But notice as I do this, there's not much change in this direction. On the other hand, if you start with a twisted Kagame lattice, you push on it, and you get the sequence, which is exactly what I showed there, and you can see that this distance right here is less than that distance. So this is the beginning of, you know, maybe there's some interesting materials we can make with this, and we're exploring those ideas. Now let's go to the spectrum of the twisted lattice. If I don't twist the lattice, I've got this spectrum where we have a zero mode running from gamma to m. I add next nearest neighbor forces, we get a gap, which is proportional to k prime. I twist the lattice, we get a gap without doing anything. I haven't added any next nearest neighbors. All I've done is to go from the untwisted Kagame lattice to the one where it's twisted, and I get a gap spectrum with a characteristic angle, which should have been, this should be omega alpha, going a sine of alpha, and a length that goes as 1 over sine of theta. So twisting has an effect which is very similar to adding next nearest neighbor forces, and it doesn't violate Maxwell, because remember, Maxwell said that we have a periodic structure, we should have no zero modes. So what's happened is we've lost all of the states of self-stress, and it's pretty clear that we've lost the states of self-stress because this lattice supports stresses for each of the straight lines. This lattice doesn't have any straight lines, and the only states of self-stress are two trivial ones which involve the whole sample. So that was a surprise, and it took us a while to understand that. There's actually a nice continuum theory that you can write down that looks a little bit like a gauge theory, where this angle phi tells you how this triangle is compressed, and this is the trace of the strain tensor, which tells you how much isotropic compression you have. So you can see you can have a non-vanishing twisting angle, which changes the size of the hexagon, and that will then drive a compression, and you're left then with, you know, if I set k prime equal to 0, this is non-vanishing. And I've got a theory, once I've relaxed everything, which is, I'll just say this now and go back to it, in which the bulk modulus is vanished. All I have is the symmetric traceless part of the strain tensor, and this has the property that the symmetric traceless part of the strain tensor is the same as the symmetric traceless part of the metric tensor. So the energy doesn't change for any distortion that leaves this unchanged, and any distortion that leaves this unchanged is a conformal transformation. So this is a conformally invariant field theory, and you can do all the tricks that people do of, you know, looking at strips and so forth to determine what the zero modes are. But let's go back and do what the calculation is. So where had the zero modes go? In the case of the square lattice and the Kagame lattice, when we cut the system, the zero modes of the periodic system became the zero modes of the cut system. In the twisted lattice, we have no zero modes in the bulk, but if we cut things out, Maxwell tells us we have to have a number of zero modes which is proportional to the perimeter. So what's happened? Well, what happens is the cut sample has zero modes on the surface, which the periodic or bulk boundary things will not give you. And these surface modes turn out to be, at the long wavelength at least, exactly the surface Rayleigh waves of an elastic medium, which have, if you calculate the frequency of the Rayleigh waves, they have zero frequency when the bulk modulus is 0. Now, of course, we're not restricted to be in the hydrodynamic limit where the wavelength is long. So if I plot q prime of x, so now what I have is a surface that's parallel to the y direction, and I look at the inverse penetration depth into the x direction. So the long wavelength elastic theory will tell you that q prime is exactly linear in qy. In fact, it's equal to qy. So these are the simulations, and actually they're not. They're both simulations and our analytic calculation, which you can do with transfer matrices. It rises linearly, and then it reaches a saturation value where this penetration depth is exactly, or where the qx is exactly 1 over that length, which goes as sine of theta. And you can see why that is. Remember that as I make the angle get smaller and smaller, I get closer and closer to having straight lines. So suppose I try to put a surface wave on something that has straight lines going all the way across. Well, in the square lattice, it's easy to see. If I push here a little bit, it's going to go all the way over to the end of the sample. It can't be called a surface wave. It's exactly the zero mode of the bulk. And the reason why the zero mode in the bulk exists is because this thing has a state of self-stress, which basically transmits stress all the way across. So this is what you expect, that as the angle goes closer and closer to 0 and you get this critical point with lines, that you will lose the surface modes. So the count is right, and that everything works. I should say that there are many other versions of the twisted lattice you can have. This one is rather interesting. We alternate back and forth between stretches in this direction and that direction. So now I've broken the symmetry in this direction. It's now a uniaxial crystal. But if you look at the low frequency modes of the system, it's exactly isotropic and behaves exactly the same way as the isotropic system. But I have zero modes out further in the Brillouin zone, and there's all kinds of complex structures here. So there's really a vast unexplored region of how do you put together all of the phonon structures of these things that have you start with an isostatic lattice, you do one of the infinite number of distortions, and then you ask, what is the phonons? Okay, so what I really noticed early on this is that you turn on this angle, and you take a zero mode, and you gap it. So you can't be in a condensed matter physics department anywhere and not have heard about topological insulators. The classic example of which, well, okay, so let me then jump to topological insulators. And the heroes here are Charlie Kane and Jean Malie, who first figured this out in the context of polyacetylene. Basically, this whole business of topological effects in quantum systems it permeates all of hard condensed matter physics. But what they discovered was that gap states, an insulator, if you remember your solid state physics, you have a band structure, and if your Fermi surface lies in a gap, then at zero temperature, you don't have any electronic states that can be excited, and you have an insulator. Nothing can conduct. And what they discovered is that when you have a gap state, there are different topological classifications of these gap states, and the different topological characterizations give rise to either states that conduct on the surface or states that don't. So you can imagine how exciting this is in the world. I mean, this has come straight out of just harmonic electron theory. So let me go through the simplest example of this. This is the so-called Su-Schrieffer-Heeger model. It's polyacetylene, where you have, in the chemist language, alternating double bonds and single bonds. In the physicist language, you have a charge density wave that runs along here. But let's just say that we have this picture with a electron hopping from here to here, which has one value for that guy and another value for that guy. And the Hamiltonian is simply this in reciprocal space. T1 is the blue hopping, T2 is the red hopping. And I can write this as QK, QK star, and it's trivial to calculate the energy. It's just the magnitude of this. And you get then when T1 goes to T2, which is the point where you've lost the dimerization, it's 2T cosine of K over 2. And you can see then at the band gaps at K equals pi or minus pi, you get a 0. So if T1 equals T2, you have this spectrum with a point there. When T1 is different from T2, you develop a gap. So that looks exactly like what we had for the phonon structure, where you have a 0 going all the way down a line in reciprocal space. In the isostatic case, we turn on the rotation, we gap it, and the modes, well, let's see. Did I have it here? Shoot. Oh, I guess I lost the picture. Okay, anyhow, you have the same thing. So how do I, what is the topological characterization of this? I can define this function f of k, which is the imaginary part of the log of q. Now, why would I do that? If q were just e to the I theta, then the log would be I theta, and the imaginary part would be theta. And so if we then integrate that theta angle across the Brillouin zone, it has to be physically either 0 or 2 pi at the two edges. And so if we do that integration, we can get either 0 or a number. So here, this shows this function as a function of k going from minus pi to pi for the case where t2 is greater than t1. I wrote k here. And when t2 is less than, t1 is greater than t2, the other way around, the function goes back and it comes back to 0. So the difference between here and here is 2 pi. Here the difference is 0. And if I plot the imaginary part of f of k, contour plot, well, this is imaginary part of k, imaginary part of k, real part of k, and k is a parameter that wraps me around here. So in this case, I enclose the origin. In this case, I don't. So I can define a number, which is 1 over 2 pi, the integral from minus pi to pi, of the derivative of this thing with respect to k, and you then just get the difference of these two functions, which has a value of minus 1 or 0. So there you have a well-defined number that's different depending upon whether t1 is greater than t2 or less than t2, or equal to t2. And then there's a lot of pretty fancy theory that says, let me consider the case where I go from one alternation to the other. So over here, I have alternation 1. Over here, I have alternation 2. And I can talk about the gap parameter, which is m. And it goes from being positive to negative, if you wish. And there is you can then ask, what is the electronic, are there any electronic states that sit right here? And what are their nature? And it turns out there is exactly one state of 0 energy that's topologically protected because I'm going from two different symmetry things continuously. And that's what people find interesting, is that you have a mode there that is stuck. It has 0 energy, and it's there because of the topology of the Fermi surface. So the insulators come from looking at graphene. The pure graphene with only nearest neighbor hopping like this has this band structure. And if I look right at these two equivalent points, in the absence of any perturbation, you have these straight lines, and you have what's called the Dirac spectrum. Then there are many ways you can turn on perturbations. You can turn on, you can put in spin-orbit couplings. You can do something to break the periodic symmetry and double the unit cell size and so forth. So basically, you then gap the spectrum. And then the question is, do these gap states have different topological characterizations? And the answer is yes. And there's basically, you either have a plus state or a 0 state. In the standard insulator, here are the bands with the gap. Here are the surface modes that look like this. Here is the standard insulator where the Fermi surface sits in a region where there are no surface states. Here, the Fermi surface sits crosses the 0 modes, the surface modes, and therefore these states right here are conducting. Right? So you can have an insulator that conducts on the surface. And there's a lot of very interesting physics, which I don't have time to go into, and I don't really have totally digested myself, about the spins, which allow these things to be protected even when you turn on interactions.
The doping system.
Well,
So that would break the symmetry between, let's say, spins.
doping will tend to, it tells you how much you fill these things. So, if you put the Fermi surface here, what you want to do is to have it doped so there's one electron per site, or maybe one spin electron per site, because that puts the Fermi surface here. If you start doping, then of course the Fermi surface is down here, and you don't overlap those surface states. Okay, so, right.
But suppose you dope it just a little bit. You move it, it's still within the gas. Gas has a finite width, right?
Well, I mean, if I dope it depends on where the Fermi where you put your Fermi surface.
Suppose you dope it just a little bit.
Oh, if I did it just, you're right. If I just filled up these guys a little bit, just a little bit being square root of n or something like that, yeah. Okay. As I said, there are lots of questions here that I don't know how to answer yet. This
So it
is,
just seems like there's a finite range of doping over which you'd only get conduction in the surface state.
yeah, but that finite range is 0 in the thermodynamic limit. Right, because how many surface states are there? There's square root of n surface states. So if I start adding things up here, I can only put square root of n sites in before I've raised it up to there. But not square root of n, it's n to the, it's the number of surface states over the volume. Because remember, this is a figure in the surface Brillouin zone, so I only have one state per wave vector in the Brillouin zone along here. Okay. So how do we get to the topological states here? I have 3.5 minutes to finish this. So remember I told you that the Hamiltonian could be written as, I wrote this backwards. It should have been QQ transpose, but don't worry. The Hamiltonian is basically Q times Q transpose, right? So looking at this, it's not obvious at all how to make anything topological. But you can introduce this effective Hamiltonian where I put the Q and the Q transpose here, such that the square of the Hamiltonian has the actual Hamiltonian and something else. So this is basically a Hamiltonian where I have an interaction between the bonds and the sites. And so now I can treat this Q in much the same way as that off-diagonal element in the polyacetylene and ask, characterize the system by the imaginary part of the log of this function, which is now a 6x6 matrix for the Kagame lattice. So this is what comes out. It's really beautiful. So remember that for each site, I have 2 degrees of freedom, and in the periodic case, I have 2 bonds. So one way I can talk about that is to assign a charge of +2 to every site and a charge of -1 to every bond. If I do that, at isostaticity, I have charge neutrality. Then I can look along a given line, if I cut it, and count the number of sites and the number of bonds and get a local charge density for the surface. So typically for these surfaces, the local charge density is, let's see, so I need to go 1, 2, let's see, I have to remember how to do this now. Yeah, so I need to count all of the bonds. So here I have 1, 2, this site has 3 neighbors. So I have a charge 2, -1, -1, -1. And go on down there, and I end up then with a net charge, which is non-zero. So we call that the local charge. Then in addition, there's a polarization charge, which is exactly the vector generalization of what I had before. So this polarization charge is exactly like having a polarization in the electric field. And when I take the dot product of that with the surface, I get the surface charge coming from the polarization, which will have a different value at 2 sides of the sample. So we can then define this thing nu, which is the number of zero modes minus the number of states of self-stress, which is the dn minus nb. And we can break this up on the surface into a local part and a topological part. This is the local count. This is the topological count. And the total value of this is ds.p, so it depends on s and the direction of p, so that the topological charge is the number of cells, the reciprocal lattice vector that's normal to the surface divided by 2 pi. And g, of course, is exactly the reciprocal lattice vector. It's the sum over n's of the reciprocal lattice generators. And a is the direct lattice things, where bi.bj is 2 pi over nij. So let's just see how this works out. So how do I then get different topological characterizations? So you saw that we had to go through a 0 in the case of the polyacetylene in going from the left-right, single bond, double bond, single bond, double bond. To go continuously to the other one where I go double bond, single bond, double bond, single bond, I had to go through a state where the spectrum went through 0. So in order to separate states cleanly, what we want to do is to start with states like this. So this is the twisted Kagame lattice, and it has no states of self-stress. What I want to do is to continuously distort it, so I introduce a states of self-stress along one direction, and then keep on distorting it so I go to the opposite side. So this guy goes to there by doing a distortion of these things, and I forget which direction, but I can go continuously from here to the twisted Kagame, or continuously from here to this opposite thing. And these two guys have different topological charges, and I can then ask what are their surface modes looking like. So here are the numerical calculations. This is the Kagame lattice clamped at both ends. This is a spectrum of the finite strip. There are no modes of zero energy down here. Here, I clamp the top, and I look at the zero modes, and there's one zero mode for every wave number along the surface Brillouin zone associated with this surface. Now, this is clamped up here, but these things are sufficiently twisted that the surface states are localized, and it doesn't feel that. So up here, I have a state of self-stress that I'm not looking at, and I get this. Now, let's look at this state. That was the one which was obtained by rotating in the opposite direction. This has a polarization of minus A2. Did I draw a picture here of that? Yeah. So here, this is lattice vector A1, this is lattice vector A2, this is A3, and these are the reciprocal lattice vectors. So P2 is minus A2, G is minus B2, it goes this way, so we have a total local charge of 1, a topological charge of 1, no states of self-stress down here, and therefore the total number of modes per wave number should be 2. And you can see there are 2 modes here. When we get down to low Q, the penetration depth is large enough on one of them that I hit the other side and lifts it from 0, but I have 2 there. And then we can look at taking this guy and flipping it around the other way. So now, down here, the topological charge is minus 1, because the polarization, remember, was pointing, the polarization is pointing something like this. And if I change the direction, it's going to change the direction of G, and that gives me a minus 1 here. And therefore, I have no states of no zero states. And that's what happens here. And finally, we can look at an interface between the 2 different states. So interface 1, we have no local charge because everything is balanced. We still have the same topological charge, so there should be one zero energy state up here. Now, of course, this is periodic boundary conditions, and I don't have, the total count is the same. So if I introduce zero modes here, I need to introduce somewhere else states of self-stress to get that to work. So down here at surface 2, I have states of self-stress, which don't give me any zero energies, but allow me to compensate for the theorem. So that's the story in a nutshell. It's still very much in flux. We don't have a paper written yet, but we can see lots of other things. If we look at these 4-state models, then we have not lines that go to 0, but points that go to 0, much as the topological insulators. You can ask what happens if you extend these ideas to random and quasi-crystalline structures. We're not sure. What happens if you take these modes and add nearest neighbor or bending forces as you would have in a real system? Will you get, say, if you try to compress one of these systems with a boundary down the middle, whether you will get failure exactly at the point where you have the line and things like that, and so forth and so on. So sorry for going 4 minutes over. I will stop now.
Thank you very much. Are there questions just there?
You look at the particular case of isostatic systems, i.e. those with central forces.
Yes.
And when you make the analogs to granular systems, this corresponds to smooth spheres, essentially.
Well, it corresponds to frictionless spheres with only central forces, and we generally, I haven't addressed the question of whether we're using Hertzian springs or whether we're, so we basically replace things by central forces.
That's not my question.
Yeah.
The point is that isostaticity is much more general than that.
Yes,
And
absolutely.
it works, of course, in frictional spheres.
Yes.
In which case, the mean coordination number in 2 dimensions is not 4 by 3. Now, in frictional spheres, when you have these zero modes, you have no Lamé constants or elastic constants, whatever. You can do it with rigid spheres. And there, the zero modes correspond to simply the whole system acting as cogwheels. In other words, you invest no energy to distort the system. In smooth spheres, it's much more difficult to see what is the analog.
Obviously, if you look at smooth spheres, then the number of degrees of freedom is not d per particle. It's d plus d, whatever the number of rotations. And those are much more complicated. So they have some of the behavior that we see in the twisted Kagame lattice, in that you have your naive count would give you a certain number of zero modes, but if you actually calculate the phonons, you don't see as many as you'd like. So I haven't followed the details of that, but there's work from Leiden and there's work from Andrea Liu's group, which has looked at that problem. Another place where this arises, and in fact is probably the most successful application of the isostatic ideas, are in glasses. The work of mostly Thorpe, but Jim Phillips and a guy named, I'm forgetting his name now, but I am told, right, I haven't followed it down, that the glass in this thing, Gorilla Glass, is a very sensitive adjustment of things so that you're right near the isostatic point, but a little bit above it.
But silicates are isostatic.
Silicates, yeah. So yeah, there's a lot that can be done with this. The idea is also, Mike Thorpe has extended these ideas to protein folding in a very successful way. So it's actually a much richer field than most of us know about.
And just here.
I'm trying to understand why the state is topologically protected. For example, if I go back to those images that you were showing with the topological charge, is that quantity invariant if I do a random shift of the position along the particles?
So
Is that
so within, so at the moment we're only looking at this periodic thing. So these two guys are distortions, and they have exactly the same topological charge. So they have the same topological charge until I hit this guy, which has then the states of self-stress, which is the ungapped part of the spectrum. Right? And then if I keep on distorting, it goes to this, and this and all versions of it have the same topological. Now, the B is always along one of the lattice vectors. And if you take the lattice and rotate it by 2 pi over 6, so in a sense, though there are 6 lattice vectors that are relevant, a rotation of the lattice will bring it back to the other. So there's really only 2 states in a sense, depending upon how you orient the sample.
If I shift each of those points by epsilon in random direction?
Okay, so we haven't done that yet. We expect that they are protected, but we haven't done the whole thing yet, right? That's part of what needs to be done. And is there a topological characterization of the jammed states, for example? Maybe. We just don't know yet.
This is a bit of a cheat of a question because I heard Fred McIntosh talk about this a couple of weeks ago, but you didn't talk about what happens to these systems if you put them at finite temperature. And I don't know how much you want to say about that.
Okay, well, I can tell you a lot about one system, which is the square lattice. And that's actually fairly interesting. So the square lattice...
So that is with only nearest neighbor.
So I start off with square lattice with only nearest neighbor. At t equals 0, it has this isostatic structure with a line of 0 modes. So what other system have you heard of that has a line of 0 modes? Smectic, right? Or the ideal liquid to crystal transition in the soft language. You get 0 modes all along a sphere, right? So that asks the question, that begs the question then, are these isostatic points a type of critical point? Right, and so we've addressed that by saying, let me add next nearest neighbor forces, and I'll make it a potential that has a 5/4 in it. So the potential is 1/2 a r squared plus g r to the 4th. And so in the and that's the potential for next nearest neighbors. So this is the point a equals 0. It's that critical point we're talking about. Right? If I make a positive, then all over here I have a stable square lattice, even at 0 temperature. And I raise the temperature, I get some thermal expansion and things like that. If I make a negative, then there are 2 different values of these cross links that it likes. So it will try to transform to that. But it could also transform to this. So this ground state over here, when G is negative, has a ground state entropy that goes like the square root of n, because once I set the configuration along one line, I fix it along all of the squares on that line. But the next one can go in the other direction. So I have a choice, a 2 to the nth choice as I go up here. So the entropy goes like the log of 2 to the square root of the number of particles. Right. So down here, I have a highly degenerate state at 0 temperature. This guy now looks like a Brzezowski point because I have 0 modes all along, and you can do a Brzezowski calculation, and you get a first-order transition where this particular guy wins, where they're all like that. And you can calculate the entropy of the different states that come up here, and you find that at any finite temperature, this wins over the random ones, so you get an order out of disorder transition.
Okay, well, I see that the wine has already been poured.
Yes.
Someone has already taken a
Let's go
joint.
for that.